This is a question on group 7 and bonding. It's 4 sections, A through to D. The first question is 6 marks, but it's not a 6-marker question in the sense that it's not leveled marking. So have a go at these, see how you do, and then review with the remainder of the video. Here's part A, part B, part C, and part D. So going back to part A, we've got 3 different structures here, and when we're talking about melting points, we're really thinking about the bonding within them. So I'm going to put this into a table actually, just so we can highlight the similarities and differences quite effectively. So if I consider how they're bonded together, the strontium chloride is ionic, it's a metal with a non-metal, but the other two are molecular covalent, and that means we're dealing there with intermolecular forces, and I'll come back to those in a moment. For ionic, we can talk about the fact there are lots of strong electrostatic forces of attraction between oppositely charged ions, 1 mark. That means lots of energy is needed to overcome them. We've got our 2nd mark. And it also, because the other two are molecular covalent, means we know that that will be the highest melting point of the 3. Now, if I move on to mark 3 now, I'm looking at ICL, and I know that there will be dipole-dipole forces. Now, they are weaker than ionic, so we don't need to put as much energy in, so the melting point will be lower. But before we put it in to our order, let's also consider bromine, which would only have van der Waals forces, by far the weakest intermolecular force. The final 2 marks are going to come from writing your structures in the correct order of melting point, as you can see at the bottom. Moving on to part B, and we've got part of the group 7 topic here, chlorine reacting with water. You simply have got to remember the equation. You've got to know that when chlorine reacts with water, you will make HCl and HOCl. It's actually a really important equation because this is one of the examples we can use to show disproportionation. It's disproportionation because the chlorine is both oxidized and reduced in this reaction. Now, we add chlorine to kill bacteria, and it's important that we give that level of detail. We can't simply say it cleans the water. It kills bacteria. Disadvantages, we've got more than one choice here. If it got to high enough doses, it could be toxic. You wouldn't aim to do that, but people could put too much chlorine in, and that would be a risk. But also, if we think about potable water, tap water, not all of it is used for drinking. So if we're using it to wash clothes and wash dishes, actually is that a waste of chlorine in water that would not be drunk? Moving on to part C. And we start off with the equation here for the reaction of phosphorus and bromine to make phosphorus tribromide. So we have the elements P and Br. We have to know that bromine exists as a diatomic molecule, and you should know from your trends in melting points that phosphorus exists as P4. Now from there, we know that we are making PBr3, and from there it's simply just balancing. I've got 4 P's on the left, so I need 4 P's on the right. I've now got 12 Brs on the right, so I need 6 Br2 on the left. And in terms of the shape, I'm going to put the dot cross diagram in red on the left hand side to talk it through. Phosphorus is in group 5, 5 electrons in its outer shell. 3 of them are being used in bonding pairs, which leaves 1 lone pair. Now that means 4 pairs of electrons in total, which means it's based on tetrahedral. And you can see that the diagram here is representing the tetrahedral structure, but I've drawn my lone pair on the top. Now my bond angle in tetrahedral, I have to remember, is 109.5 degrees, but a lone pair causes some disruption and it will reduce them, we normally say, by around 2.5 degrees. So I would be hoping you'd put down the answer 107 degrees. And finally, on to part D, we've got phosphorus pentabromide, which is PBr4 plus and Br minus. But actually the question is asking about the PBr4 plus. And the PBr4 plus, well, we saw there was a lone pair on the phosphorus. So we're forming a dative covalent bond. The dative covalent bond now means there are 4 bonding pairs and no lone pairs. So this actually is tetrahedral. and the bond angle is 109.5 degrees.